Good afternoon, everyone. Thank you all for being here for this next webinar in our series focusing on digital learning tools. My name is Jeff Bertrand. I'm the Director of Visualizations for Clemson University Center for Workforce Development. And today I'm happy to introduce Dr. Erik Verlage from MIT. I first met Erik at a workshop for workforce development about 2 years ago. And a couple months after that, we teamed up with some folks from the University of Arizona to create some digital learning tools for training technicians in fiber optics and integrated photonics. And we had quite a lot of success so far. And I briefly touched on this project in the previous webinar, but today Erik's going to go more in depth into it and look at the project as a whole. So we will have a Q&A session at the end. So please feel free to write your questions or comments in the QA section of Zoom. And with that, I'll hand it over to you, Erik.
Hi, everybody. So I'm Erik Verlage. I'm a research scientist at MIT, and I'm working on leading this effort called the Virtual Manufacturing Lab. And so it's a cross-university, we're calling it a design house for interactive digital content, and we're creating all of our content that's focused on advanced manufacturing, targeting the Manufacturing USA Institutes. And so it's a partnership between MIT and then our partners at CUCWD at Clemson University, who you're very familiar with, and then the University of Arizona, all as part of AIM Photonics Academy, which is the education and workforce development arm of the AIM Photonics Institute. And so a lot of our stakeholders who we're actually developing content for are the Manufacturing USA Institutes that were established during the Obama era, specifically focused on US manufacturing. And it spans many different fields. So there's our field of integrated photonics for AIM Photonics. There's functional fabrics, which uses fiber optics in wearables and clothing. There's ARM for robotics. There's BioFab. There's NextFlex. So all these MUSA institutes that we interact with. In the first 2 years of our project, we're mostly focusing on optics and photonics. So you'll see a lot of our content is optics focused. But we're in year 3, starting this October, we're going to expand out to include other Manufacturing USA institutes. And so what we're doing is we're developing content, normally desktop VR simulations or interactive simulations, digital simulations, specifically for the edX and OpenEdX platforms. So we're currently standing up our own OpenEdX platform that has a military focus, and we're also putting up our content on Educate Workforce, Clemson's platform. And we're also using all of our content in a lot of different programs that we have, specifically a 15-month technician training program that we've been piloting at different community colleges that are our partner institutes. So without further ado, let's go into what our project is about. So we've been kind of having a 3-pronged effort to create interactive simulations and games that are going to be useful for educating the workforce in advanced manufacturing. And so we have these 3 different categories of simulations that we're developing. There's the kind of micron scale optics and photonics fundamental simulations, where we're trying to give students an understanding of optics and photonics on a small chip or inside of an optical fiber. And so this is actually, and in the future, we want to expand out to fundamentals in other fields. So maybe this the fundamentals of material science for let's say flexible electronics or other things that are on the micron scale. And so we're really trying to give students kind of visualizations that help them to understand what's going on at the small scale and to understand kind of basic principles and concepts. So then Jeff's probably already shown you many simulations that we're developing where we're trying to then give macro scale tool training experience for technicians who might be working on the fab floor or anyone else who might be using this equipment in a research or manufacturing capacity. And so what we're doing is we're really trying to create training simulations that are modular, that are kind of like a one sitting simulation where you can maybe the night before you're going to be trained on a lathe or a draw tower for fiber optics manufacturing. You might run the simulation and get to know what the equipment that you're going to use ahead of time. And we're really envisioning that this would be something that would interact well with the fundamental simulations where you can learn the tool using. And then finally, I'm going to go into a very fun topic where there's many people here at MIT who are working on educational games and how this can be used for training purposes for an adult audience. And all of our content is either being put into a series of online courses that we've been developing. So we have many subject matter experts who are creating their own courses. And so we're developing this interactive content that will plug into a course. So for instance, we have a instructor who's creating a photonics course about chemical sensing and to sense methane and sense other, and also biological sensing using optics and photonics. And so we created content that can fit into her course at the very beginning and then at the very end. And so it's kind of it's supporting all of those efforts that we have for standard courses. And then we're creating simulation libraries that can then be accessed by students on an ad hoc basis, so they can do it at their own pace. And if they want to learn about a specific topic, they might dive into one small module and then learn a little bit about it, and then switch over to something else. I'll just quickly, I'm going to go through all three sections, and I'm just going to give you an overview of all of our activities. So for the micron scale simulations, the optics and photonics fundamental simulations, what we've been doing has been trying to really design a scaffolded approach to having students switch over from kind of a ray optics perspective of light, where they think about light as like rays bouncing around inside of a material or bouncing off of surfaces like mirrors, to really starting to understand kind of the fundamentals of the field, understand guiding of the modes that are guided inside of an optical fiber or a micron scale waveguide on a chip for the field of integrated photonics. And so here we're actually trying to give students kind of an understanding of the vector field nature of electromagnetic fields, and to understand how like different modes are supported, kind of the quantum nature of light on this scale, and also to understand the different optical devices that are now kind of becoming commercialized in integrated photonic circuits. And so this is just our bread and butter. We're very excited about creating content that's kind of new and visual for students to kind of grasp new concepts. And we've been kind of really focusing on creating a progression that builds up their understanding from the ground up. And so I thought you might be interested in kind of how we're doing this. So we're actually using photonics design software. So this is commercially available software that a lot of instructors will use in their courses, but as you can imagine, there's kind of a cognitive barrier. So the cognitive load that students have in trying to learn a very complicated and complex tool, it's as if you threw them into the most advanced flight simulator on the market, and you're saying, hey, you want to learn about the principles of flight? Here's the most advanced simulator with all the buttons and knobs all around you, and you're like, here's the manual for how to use the advanced simulator. And so you might really not get much out of that session. Whereas if you gave them kind of an RC plane and say, here's the 3 knobs you can turn, fly your little plane around, and you can learn about pitch and yaw and wind and all these other factors, that's what we're trying to create here, where these photonics design software tools are just too advanced, too difficult to use, and you can actually create artifacts, so like the data you get might not be actually accurate. So what we've done is instead try to transform all of this data using different processes into visualizations. So we run the data ahead of time. We develop a database that the simulations then use as a lookup table, or we develop the rules that then the simulations use to showcase different optical phenomena on the micron scale. And so you can see that we've been developing all this content to be put into the Unity game engine. So we use either having JSON arrays or images that we then import into Unity. And then we use the Unity shader to create the visualizations that have the optical, have the like very accurate optical models, results from the optical models. And you can now use that as part of the simulation. So I thought that would just be an interesting thing to show you. I don't expect you guys to follow the optics, but we're having a lot of fun creating these data visualizations. The thing I can touch on is the desktop VR simulation. So this is what we're working very closely with the CUCWD and Jeff and Couple and the team at Clemson. And so what we've done is we've created some procedural simulations. So in the first year of our project, which was from October 2019 to October 2020, we developed a procedural simulation to train students in how to operate a lathe for fiber manufacturing. So what they're doing here is they're taking a tube of glass, depositing materials on the inside of it to create a higher index material, then collapsing the tube that will then become a rod of glass that will then be drawn into optical fiber. So in the end, you end up with very thin strands, kind of after you draw it down, with like a very thin inner core that is like a little denser material, higher index material, and then the outer cladding, which is the original tube, the original glass from the tube, and that's the optical fiber. So that's how you create optical fiber. And we wanted the students to be able to digitally create the preforms that are used in this process. So we ended up splitting the simulation, and Jeff and his team have probably shown this to you, but there's a terminology phase where they learn about the equipment that they're going to use. There's a guided practice phase where they then go on and actually are guided through the whole process and use all the tools that you need, and end up increasing temperature, having flowing the gases, and then watching the soot be deposited on the inside of the tube, and then collapsing the tube down into a rod. And after that, once they have completed the process, we open it up to be an open exercise. So they go do it again, but this time there are hints that guide them, and there are errors that show up if they do something wrong. But the idea is that they have now learned the procedure and can do it on their own. And Jeff has probably told you a bit about the research that they're doing with this simulation. So they're doing a controlled study that focuses on how this virtual reality browser-based simulation works compared to other learning methods. So I won't go into much detail about that one because I want to focus on the other aspects of the project, but happy to answer questions afterwards. And our goal with having this all be part of the same project, we really are wanting students to be able to go back and forth between these different learning modes or these different types of simulations. So our goal is to have a student who might be learning about the operation of the lathe to then wonder, okay, well, once the fiber has been created, what are the properties, the micron scale or optical properties of the fiber that I've created? What are the guided modes that are allowed inside of a certain fiber or inside of something else that you might manufacture? So we really want to create kind of a simulation library that allows students to go back and forth between these different types of learning, both focusing on the fundamentals or the material science or the optics, and then going back and looking at the tool training that they need to operate the equipment. So we think that's a very powerful combination of different types of simulations. And so the final, this year, so for starting in October 2020 and going on to this following October in 2021, we've been working on making an advanced version of the fiber lathe. So now we've actually started to add sort of objectives to the simulation where you get to have control over the different parameters. So a student might we give them specific tutorials that take them through how to design your own recipe for these type of fiber preforms. But then during the simulation, they might have many options to choose from. We might ask them, create a single mode fiber, create a multi-mode fiber, create a graded index fiber, and they all have different properties that the student might be trying to achieve. So what we've created is kind of a game that's a crafting simulation where you have a tool and you are allowed to explore changing all the different parameters of that tool and in designing your own recipe. So we've created a user interface that allows them to build their own recipes and have like step 1, step 2, step 3, where they'll learn from trial and error. When you don't have a cladding deposition before a core deposition, then the surface is rough and you don't get a good deposition. Or if you ramp up the temperature too high, all of a sudden the glass starts to balloon out, or it gets offset and then it starts to blow up. so we're allowing them to explore the limits and the properties, the fundamental properties of the tool, like how does temperature affect the glass, or how did the flow rates affect how much material is deposited, these types of things, so that they can start to kind of explore the environment and observe and understand the tool on a deeper level. That way they're not just following a series of steps where something goes wrong, they can't really diagnose the equipment. We want them to understand, hey, if you see this, maybe this might be the cause. Maybe you forgot to turn on the one gas, or maybe what happens is something is going wrong at a certain step of the stage of the equipment. So we think that for advanced students who are already familiar with the standard procedure, having this knowledge of the tool might give them additional insight to be able to diagnose and troubleshoot their equipment if it goes wrong, and also look at the data coming out, the refractive index profiles of the fiber preform, to see, is this what I would expect, and if something's gone wrong, what might be going wrong, so they can raise the red flag to the engineer to come over and say, hey, there's something going wrong with the equipment, and I think it might be this element that's causing the failure. So we're really trying to give students the ability to explore the system in full and be able to build an intuitive model of how the tool works. Okay, so I'll jump into what I'm going to spend the majority of the time talking about today, which is when we go even beyond just kind of having interactive simulation that has game-like elements to full-on educational games. And so I'm excited to talk about the idea of going to a full game for educational purposes. So first, a definition. I guess many people have different definitions, and I've talked to people who have who even at educational conferences about game-based learning, people come with different definitions, but I'll take a stab at defining it. So for me, when I think about a simulation, it's something that is kind of has an emphasis on like real world accuracy, where it's trying to recreate something that might be in the lab or some piece of equipment that you might be using. It's normally pretty dynamic. It could be pretty complicated, but again, it's more of a tool or a toy that you might play with than something that is giving you a purpose or something that you want to do. So few inherent goals, or at least the goals are very well defined in a very specific context, and minimal narrative and identity. So what I would say, kind of going into more of like something that would be called a game, is that you're actually trying to really engage the user, maybe even try to engage them in terms of some type of fantasy or some type of creative endeavor. There are specific in-game goals, and you make decisions. So maybe there's pros and cons to doing things a certain way. There's player autonomy. There's also like levels of abstraction. A lot of times when we think of simulations, it's trying as much as possible to make it as accurate as possible, like a flight simulator. But when we think of games, a lot of times these things are abstracted away, and you might have like a much simpler user interface, or you might have something that's kind of oversimplified, but still can give across a specific like learning objective if it's an educational game. And so, yeah, I think the idea here is to see what we can do in creation of games to both build so that students can kind of have a narrative that they're following, they're kind of identifying as a person in the game, or as a character in the game. And so another definition, so gamification is more, we use that word when it's more of like you're taking an activity that you wouldn't call a game and just adding game-like elements around it. So like badges for exercising might be an example of that. So exercise exercise itself can be made into a game, but adding badges that you ran a certain number of miles, you get a badge. That's what we would call gamification. You're adding kind of like a game on top of some other type of activity. And what the MIT Education Arcade, one of our partners at MIT, and others try to do when they create educational games, is to actually make the activity itself, or the thing that you're going to be doing, be a game that could lead to educational outcomes. So in this case, instead of trying to give badges for exercising, you might actually create an activity that is exercise that is fun to do, and that incorporates other types of game elements. And so, yeah, I think the idea here is that we can use both are useful to use for different purposes, but what we're trying to do is really trying to use kind of inherent aspects of some activity or some learning activity that would be useful to have as in an educational context. So another brief pitch for why we might want to do this. So a lot of times what researchers will talk about is that games are really, really good about kind of bringing you into a flow state. So when people play games, normally, especially for entertainment games, they are really wanting to have a good time. So they are trying to get into a state where it might be challenging, but they are having fun while doing it. And so one thing that games are really good at is staying within this kind of flow, staying in the flow section of this graph. So you can imagine that if someone starts playing a game, and right now they start with their skill level being pretty low, if the game goes too slowly, or if they stay on the same level for a long time, their skills will increase, but eventually that becomes boring. So if you keep on doing the same thing and there's no extra challenge to the game, you would go into this level of boredom, you might quit. Another thing that might happen is it might go up too fast. So let's say you come in with no skills, you play the game and it ramps up immediately. Like the second level is now extremely challenging. Then you'd be going up into this level of anxiety. You're no longer in a state of flow. You're not actually having fun. You're just like, I can't do this. And so that's another area where people might quit. And so the idea when you're creating games and for entertainment games, they are definitely held to this. Other people will not buy the product or will not play if they're not experiencing a kind of a flow state. Is that you want to maintain some path within this flow region. So as player skills increases, you want the challenge to also increase. And also, I mean, this research paper talked about a zone of proximal development, where up here, this might be an area where players are, it's challenging enough that they're barely able to do it, and they might need help to do it, but they're still engaged and still having fun. And so these different paths, if you're going on a path where it's very little challenge, it might actually take a long time to build a skill. So you might have a low slope. Whereas if it's extremely challenging, you might be able to have a very rapid increase in skills and still not be in that anxiety state. So basically, one of so given this, and given the fact that games are really good about challenging students and keeping them at a level that is challenging to them, one thing that we definitely have an argument for using game-based learning is that it's very motivating for students. So students are very excited about using games for learning, and as long as the learning outcomes are embedded in the game, then they will be going towards that outcome. There's also a framework where we talk about player engagement. So there's different ways in which players will engage with a game. So they can engage cognitively. They can be thinking about how to solve a problem. They can engage emotionally. So that's another thing that students will kind of see themselves or see a character and connect with those characters in the game. They can be engaged behaviorally, maybe they're doing something with their hands in a more active game. And also they can engage in a sociocultural type of way. So the game's theme might be something that has ties to identity and to socioeconomic questions or problems in society. So just this is something that games have access to that is not normally part of our educational content. And so this actually ties into something that we're really using games for, which is identity building. A lot of students that we're really reaching out to, especially technicians coming in to a new field in STEM, might not think of themselves as math people or as science people. And they might have, especially if they're met with a challenge that they can't overcome, they might actually have a lot of baggage that they bring to the table emotionally and not be able to overcome that obstacle or feel bad about it. And one thing about games is that they adapt to the user where they are by having the level progression sort of slow down to the pace however the student is going. You don't beat level 1 until you can get these skills. And they also have graceful failure. So if a student fails at level 1, normally the kind of context of games is that that doesn't mean that you're an awful player and that you're not meant to study this material. A lot of times people come with the idea that they've played games before where you fail a few times before you get it. So it's a great thing that they bring that context to the table already. And so graceful failure, where people don't see that as indicative of that they don't belong or they shouldn't be trying to achieve these learning outcomes, they might actually be invigorated by it. It's a challenge. I'm going to rise to the challenge and actually complete the task. So cognitively, there's a lot of benefits to using a game framework around something that students might be using. So with all that background, I'll kind of showcase two of our games that were being released this summer. So we came with the idea of trying to create games that were photonics specific and also showed how integrated photonics, our technology, and optical circuits might be used in the real world. So we created these application-focused educational games that are specifically trying to be kind of a hook that brings people into the field and gets them excited about the applications of these technologies. And so game number 1, the Hypersky Data Center game, I'm going to show you kind of the progression of how we built it. And then I'll also show you an example of another game where we're having them actually design optical circuit components. And so we ended up having a large design team and a large number of people working on the project. So the MIT Education Arcade are the game-based learning experts here on campus, and we have 2 game designers who came on board to work on these games. We actually contracted out to Firehose, so we had an external contractor who had ties to MIT, who were actually the developers who built the game. And we had our own internal team of prototypers, so we had 2 developers who helped with prototyping of the game in digital form before we handed it off to the Firehose team. And we had a large number, maybe way too many subject matter experts who were all excited about this project and wanted to get in on helping to design it. And so we had many interviews in the design process. We had many interviews with the game designers where they got to understand what are the main things that we want to get across in this game. So here's an example of how you might, the process that you might use for game development. And so in pre-production, you can see that there's quite a bit of user testing and iteration. So one thing that I believe that might not happen much with VR simulations is the paper prototyping stage. So after the initial research, the game designer comes up with like a game mechanic and how it would work. It's much easier to just use index cards and note cards and just create that process. So do some user iteration on how the game would work in paper form, way before you even touch a computer or try to create the digital prototype. So, and then once the digital prototype is made, you can then iterate again. And then during production, once you have everything lined up and you know exactly what kind of game you're going to create, then we take it over to the Unity developers and actually have them try to build out the final product. And even at the end, once you have the design, the final game in digital format, level design is something where you can, again, iterate on the process. So you can be able to actually create different scaffolding for different users, or you can figure out that something's a bit too hard in the beginning, change that element out and put it later in the level progression. So there's a lot of flexibility and a lot of freedom for the game designer to change what the final product would be, even after the development has already occurred. And for our purposes for the VMLab project, the educational games that we've created, we are then going to try to incorporate it into an online course setting. So we create video content that goes before and after, and we create, and we are actually inserting this into some of our online courses, as I mentioned, for specifically for our sensing course. The sensing game is going to be one of the first things that the student sees as they go into the online course, the 6-week course. So yeah, I think we're currently in this phase where we've already done the production, and we're now doing the level design for both games. So I'll give you a brief overview and just kind of show you the process that we use in order to create these games. So we had many interviews with our subject matter experts where we talked about when managing a data center, what is it that users normally, or that people will normally think about? What will they go through as they look at data center and for the operational team when they decide which technologies to incorporate in the new data center that they're going to build. And so we also looked at how do they visualize the data during operation? How is the data center how do the data center operators look at the information that's coming to them from day-to-day operation, and kind of use that as a jumping board to see what we might create in our educational game. Then Rick Eberhardt, our game designer, created his prototype. So you can see we used index cards, and we used an idea of this kind of grid where you'd be building racks to meet certain demand, and there might be jobs that might be coming down the line. So he built this paper prototype and then tested it with many users. So we brought in technicians and others who we think would be and other undergraduate students who would be playing the game in its final form. And we found out, like, what do they find fun, what do they not find fun. And it was very easy to switch things out. You just make a new index card or change something on an index card to see if that would work better or not. So the flexibility was really impressive to see as the game designer was able to make changes on the fly and change what's going on in the game. And so yeah, he had ended up with a final version of his paper prototype that he was happy with and ready to implement it into the digital environment. And then at that point, we mocked it up, and we ended up giving it over to our digital prototyping team, and they were able to create a digital prototype of what it would look like. And at the very end, once we had everything, once we handed it over to Firehose Games, our game developers, this is sort of the final product that we created. So you end up being able to select jobs, which jobs you want to go for. There's a whole tutorial sequence that tells you how it all works, but you're able to build out the racks that you want in your data center, install new switches, install cables, and you're able to upgrade all of the different technologies inside, like the different switches and the different servers inside of your data center. And this is an interesting feature that he ended up designing, where you had a treadmill that showed what technology was coming down the line. So normally when we had our interviews, with the subject matter experts, they might tell us they know, like, 5 years out, this is likely to be the technology that's going to be available. 3 years out, here's the technology that's going to be available. So we tried to recreate that in this digital environment where you can research a technology ahead of time if you want to incorporate that in your data center. But then when you do, and when you do, you have the ability to use it in the next cycle. But if you wait for it to go to market, then you have to pay a licensing fee. So you can see that this is a pretty complicated and complex environment that they're exploring. But because it's in a game format, we're allowing them to kind of explore it on their own, learn the rules of the game on their own time and as they play the game. And if they play with multiple iterations, they might try different strategies. So they might try to build out and just have more racks to meet the demand for the jobs, or they might try to spend all their money in trying to get better technology and then build up in that way. And so you can see that by creating this environment they're going to be learning in, they can learn new things each time that they play and get a different sense for what the different technologies are allowed. And for this game, we specifically wanted them to have a historical perspective of what was going on. So the way in which we built this game, it was like technology advanced over each round that you played, and you got to see as optics got inserted into the data centers, first optical fiber, and then at the end of the game, integrated photonics, our technology. You got to see what were the advantages and disadvantages. And in this case, they got to understand that when you have copper wiring, it's cheap to transfer data over small distances, but the further away something is, if you're using a copper wire to transfer data, it gets much more expensive, and you have to use more energy in order to transfer the data. Whereas with optics, initially, the cost of going from electronics to optics was very high. So you end up having, it doesn't make any sense to use optics on that small scale. But over time, as it gets cheaper to transform an electronic signal to an optical signal, and then to transfer that information over optical fiber, all of a sudden, optical fiber makes more and more sense for smaller length scales. And at the end of the game, once it gets cheap enough, then once you go to optics, you can go, you basically get distance for free. So once you shine light down an optical fiber, it just keeps traveling along the optical fiber until it attenuates. So, but you can go very far distances. So these types of learning objectives that we had in the game is what students will gather as they choose which technologies to incorporate into their data center and what the pros and cons of using that technology are. And so I guess in the time I have left, I'll just give a brief overview of the photonic sensing game that we're releasing. So in this situation, we are having them actually design their own optical circuit. So once the information reaches or light reaches a circuit, you might have a laser source on the outside giving light to your chip. Once you can get the light onto your chip, you're able to do different things with it. In this case, we were looking at methane and seeing like what light does methane absorb at, what wavelengths of light does methane absorb, and then you can use that in a circuit on your chip. So to have a kind of a lab on a chip chemical sensor, where you use these spirals to make sure that you have a lot of distance over which the light is interacting with the material, and you expose you have light that goes through different paths that are exposed to different materials. And once you coat your circuit in a methane attracting chemical or surface reagent, then you can have all of the light interacting with methane and being absorbed if methane is present. So once you test it with methane present, we're able to see that on the path that is exposed to the environment, you end up having this large drop in power, and on the path that wasn't exposed, you do not have that large drop. So now you've created a sensor that can detect whether methane is present or not. So yeah, these are the types of things that we're trying to build. These are the first two games, and we have a second set of games that are going to be coming out next year. Oops, I think it's switched over. And so yeah, so I hope that was something that was interesting to see, and you can. I hope you enjoyed looking at our game development process and seeing all of the content that we're creating together. And I look forward to working with other MUSA institutes in the future. So coming this October, we're going to branch out to other institutes and have different fields start to create this type of content for robotics and flexible electronics and other areas of advanced manufacturing. So thank you. I'll be happy to answer questions.
Thanks so much, Eric. I really appreciate that. I put a note in the chat, but then we've also got QA as an option. So if anyone has a question, I know that Dr. Verlage would be happy to answer that. Well, also, just to let you know, Eric, we're recording this, so we'll be putting it on our website. And so we'll have the option for you to get some feedback in that way too. But really appreciate the partnership. I know Jeff and Kapil have enjoyed working with you and your team. It's nice to see some of the things that our collaboration have actually put out. So that was very helpful, and especially for our team and some of our audience who were not familiar with this project to understand. Any questions? Well, we've got a quiet audience today.
Well, I guess I have a question for everybody here. Have you ever, I guess I know that Clemson University has sometimes incorporated a few game-like elements into their simulations. And Jeff, I saw recently there was you guys had a like underwater exploration game. So I'm glad to see that yeah, you are also branching out into creating more game-like simulations. But yeah, so what's your experience been so far in creating educational games?
Yeah, the underwater ROV simulation is like our first one that's explicitly a game. So the idea is for students to go out and hunt for these sea stars that are affecting coral reefs. So they earn points within a certain amount of time. So we set it up to where they can compete with other people throughout the world. So their score will be uploaded to a leaderboard. And actually, that's going to be my question for you is, have you thought about incorporating any multiplayer elements into your app games?
Yeah, great question. And we discussed it, and we came to the conclusion that that for these specific games, it maybe was better to design it for just a single player and to maybe not care so much about scores, since we didn't want people to get. It was supposed to be the hook for instance, for the sensing game. It was supposed to be the hook to bring people in to then get them excited about completing the rest of the course. So we didn't want to get them too invested in just continuing to go on that first week's content and not pay attention to the rest of the course. So we thought it best to have it kind of feel like you get to a point where you're at the end and you're moving on to the next set of content. But yeah, I think that's a great idea for a lot of educational activities, to have it be a community, to have there be like a leaderboard or some other way to interact with others and to see what everyone else is doing. Those are things that we were excited about as well, and that would be really, really nice to include. Yeah, and the other thing is that the group that we work with, the Education Arcade, a lot of times designs educational games for the classroom. So they really do think about creating games that are multiplayer in the moment. So it's not just that you have you do your activity or you play the game and then see what everyone else has done. They actually have designed, for instance, a like cell exploration called Cellverse. It's like a cell exploration game for teaching biology to K through 12 students, where they are able to explore the inside of a cell that is sick, and they have a person on a tablet who's directing the person in the headset to look around to different areas of the cell and to try to solve the mystery of why the cell is dying and has a specific problem. And so the idea there was to really give students the ability to see kind of in full 3D space the insides of the cell, rather than just like a static image of like the like different cell components, like the nucleus and the ribosomes and all that. By seeing like there's ribosomes everywhere in this 3D world, like they can really get a sense for the cell and are able to have two people interacting while they explore the cell. So that's another way to kind of incorporate it in the classroom.
And Eric, you do have a question from Lisa. I think you can probably see that in the QA, but
yes.
She said, I know you're working on a 15-month pilot. Will this be a certificate or a degree once the students are finished? And then the follow-up was how many students will be in the program at a time?
Right. So that was we won a MEP award at the same time as CUCWD won their MEP award. And that was to create the 15-month technician training program. And so that program was specifically, we had 11 students completed it the first year. They are complete, actually right now doing their capstone project and gonna give their final presentations in a week's time. So yeah, so it was a program that was specifically for training optics technicians in Massachusetts. And right now that we ended up incorporating a few of our simulations into that program. And I believe that right now what we're giving them is a certificate, but we're still trying to work out exactly how this would scale. So this was the first pilot program that we had the optics technicians going through, and it ends in an internship where they get matched with a company and are able to then hopefully get hired on as an optics technician. Yeah, and I believe we're still working out. Sustainability was a huge problem towards the end, where we had the optics societies, the professional societies, funding the first cohort that went through the program, and now we're trying to figure out how does this actually scale and become something that can be can go on into the future without that support. So that's the major hurdle that we're working on right now.
Yeah, hopefully you can. That's always the trickier part, is the sustainability. But that's excellent that you were able to have 11 students to pilot.
And I was the final instructor, and I used a lot of our simulations in my course. So I had a month-long course that I was giving to the technicians in our program, and that was pretty fun to do.
Oh, great. Other questions? We've got a few more minutes if we have other questions. Jeff or Andrew, anything else you wanted to ask?
So there's another question in the QA about how many students would be in the program. Did you answer that?
Yeah, it's designed for up to 15 students. This would be for our 15-month technician training program. But for so the 15-month technician training program is the only in-person course that we've put our content into. The virtual manufacturing lab is creating content mostly for our online courses. So in our online courses, we've had in multiple iterations of one course, we've had somewhere around 300 to 500 people completing the course at the end, and I guess 1,500 or so people signing up for the course in the beginning. And that included these micron scale simulations, the ones that are photonics engineering focused. And we have something like five courses that are most of them asynchronous, but one of them synchronous course that we're delivering this year. And those will also all have content that we've developed as part of this program with our interactive simulations. In terms of the technician training, with using the online learning platforms, actually, that's Jeff and I had a meeting earlier, just this past hour, with a couple in his team about how we're going to be delivering this content on the Educate Workforce platform. So the technician training content will actually be an asynchronous offering on Educate Workforce.
Perfect. And for those who don't know, that is the Center for Workforce Development's learning management system. And so we will be excited to house that content for other folks to access. So, all right. Well, I think we're at a good point to wrap. Again, Erik, thanks so much for the time and a great presentation. Really enjoyed talking to you, where we can do some one-on-one outside of our roundtable meetings where we don't get to talk too much. So
that's right. Yeah. Yeah, and thank you so much for inviting me. I'm always love talking about these things. You can tell we're pretty passionate about creating all the content that we're building out, and I look forward to interacting with many of you in the future.
Yeah, absolutely. All right. Thanks again. Have a great afternoon, everybody. Thanks for joining.